So we ended last lecture with a few promises I made, and now I'll try to convince you how deep learning can live up to those expectations. So first, I'll give a brief review of backpropagation. Those of you who did machine learning maybe remember about this. And then I'll talk also about stochastic gradient descent. This is the basic method for training neural networks. And then we'll see a bit more about what deep learning can do for us, in particular related to unstructured data. And also I'll try to explain why the recent success in deep learning. And we'll finish with some examples. So we'll start with the basic method for training neural networks, which is backpropagation. This was actually used in the 70s for other kinds of problems, but in the mid 1980s it was discovered that it could be used to train stacks of neurons or networks of neurons, and that's how artificial neural networks started. So they were initially also quite popular, but there were some problems. We'll see a bit more about that. But this is the basic element and basic methods for deep models. So we have this neuron model that was inspired in the biological neuron, but mathematically you have a weighted sum of the inputs and then some activation function that is nonlinear. And this, remember, is very important because the power of nonlinear transformations for increasing the ability of our classifier. And why is this important in the neuron? In a single neuron, it's not. As you saw in the perceptron, we can just check if the output is above 0 or below 0, and we don't need anything else. But the perceptron can only do linear classification. What happens is that when we chain neurons together, then the ability to do nonlinear transformations at each neuron, the nonlinear outputs, is what makes the chain of neurons different from a single neuron. Because if all of them were linear, then you chain linear transformations and you just get a linear transformation with different weights, but it's the same thing. So this is an important part for our ability to create nonlinear classifiers by chaining together these elements. So this is the basic piece. We can think of the initial perceptron activation function was just this threshold function. So if it's below 0, it's 0. If it's above 0, it's 1. There is, however, a problem. You can do this. You can create that training algorithm for the perceptron of just adjusting the weights when it makes mistakes, but you cannot chain together different perceptrons like this because then you don't know how to adjust the weights. What we need is something that is similar to that. At least this was the initial intuition. We'll see next week why it was wrong. But we need something similar that can be that has a continuous derivative. We can compute the derivative everywhere. The derivative behaves nicely, and this was the general idea. We have something that is that can be differentiable everywhere and with a nice derivative. And this is the the sigmoid function, the same we use in logistic regression. So actually, this neuron for a long time was very similar to the same model for logistic regression, but we just kept adding them in chains. But let's see how we can train a single neuron with that activation function. Suppose that we have this error function that we want to minimize. This is the quadratic error between the output of the neuron and some target value that we want. So we take the difference between the target and the output for each example. We square that difference, and then we add for all the examples, and this is the total error. This 1/2 here is just so that when we compute the derivative, it cuts out with the 2 there, and we have a nicer expression for the derivative. Now, what we can do is we can compute the error here, outside the neuron. This is a quadratic function, but we can compute the derivative with respect to the output of the neuron. But then we can continue our derivation in chain, so we can compute the derivative of the output with respect to the activation function, and then with respect to the weight, and we do the update. So this is what we do here. We compute the derivative of the error with respect to the weights, because the weights back there is what we want to update. And we want to update them in a way that reduces the error. So we want to go down the derivative of the error function. But to do that, we have to go through all these intermediate steps. But, okay, this is just this set of equations. We compute the derivative of the error with respect to the output of the neuron, the derivative of the output with respect to the sum, to the weighted sum of the inputs, and then the derivative of that weighted sum with respect to each weight there. And we have, if we have a sigmoid activation function like this, then these are the derivatives for the error, the activation, and so forth. So with a quadratic error, a sigmoid activation, and then the derivatives for the weight. We don't need to go into much detail for the equations, but the idea is that we can do this. They're all continuous functions. We can compute all the derivatives and chain everything together. And so this tells us what is the variation we have to put on the weight to go down the error surface for that particular example. So the intuitive explanation is simply that we're going through all these functions, the logistic activation function, the sum here, and the products there, and we are computing the derivatives all through those operations. So now what do? We have one example, we can measure the error, we can compute the derivatives, and basically we know that if we are here, then the derivatives are pointing this way if we want to go down the surface of the error function. So what we can do is we move a little in that direction, and then we present a new example and move a little in another direction, because that new example will now have the different error and so on. And we keep moving like that until we reach the bottom. So this is gradient descent, because for each point we are computing the derivative, the gradient of the error function, and we are going down that gradient. And it's stochastic because we scramble the order of the examples, and at each step the network can be seeing any example in random order. So the actual trajectory here will be random, but it will be tendentially downward. Okay?
What will be the limit of the error?
Not necessarily. The value in the limit will depend on how well the model can adjust the training set. So if it's possible to get the outputs exactly like the target values, then in theory you could reach a zero training error. But maybe your model cannot approximate it like that. And this would be in theory, because in practice, if you reach a region where the derivatives are very small, then training starts taking a long time. Because the derivatives are small, you can only change small steps at a time. So in practice, what happens when training neural networks is that at some point the loss function is not going down. We don't know why. Maybe we're at a minimum, or maybe we're on a plane and we cannot get out from there, and we just get bored and stop training. So that's what happens in practice. When the gradients are too small, training eventually stops because it doesn't pay out to continue training. But the error depends on the data and the model.
And that will be our result.
Yes, the sets of weights that you have trained. So another way of doing this, because if you present one example, you have one estimate of what the error function looks like at that point and how to go down the error function. But in a more rigorous, or in practice, what we really want is not the error of each individual example. It should be the error of the whole set of examples. So one example gives us the error for that example, and we can take the derivatives there, but this is not the whole picture for the whole set. So we can get better estimates of the direction to go down if we take a batch of examples, we put all of them, and compute the contribution to the derivatives from all the examples, and then give a step in that direction. This is also an advantage because it saves computational power. We just need to do this, for example, for a whole lot. It can be more practical when we use GPUs and something like that. But because we're not constantly changing the weight of the network, we're just computing the derivative for all the examples and then change one for the lot of examples. However, if we use too much examples, then we start losing some information about the individual steps, and we lose this ability to go down in a random trajectory, which is also important to escape traps, holes in the function that would make everything get stuck. So this is the general idea, stochastic gradient descent. We'll see this in practice, how this batch learning or mini batch learning is used. It can be useful also for other things, but there is a trade-off. If we use batches that are too small, we don't have much information on each batch, and it takes computationally it's more demanding because we are always updating the whole network. If the batches are too large, then we are averaging too much over the examples, and we lose this ability to zigzag through the traps to reach the best point. So typically in practice we use batch sizes of 32 examples, 64, something like that. If you have a very large model and data with many features, there can be a limit to the memory on the size of the batch, but that's usually the kind of values that we use. Okay, so using this we can train a single neuron. We have these examples. We present some examples, we compute the derivatives, and we use that to adjust the weight. And as we present examples to the neuron, the loss function will decrease, and it will start to learn where to classify. But since it's just one single neuron, it cannot classify all those points correctly, because it can only do a straight line. So we need to go further and chain together different neurons. If the output of the neuron was linear, it would not make any difference to chain neurons together. But since each neuron has a nonlinear function, when we chain them together, we start increasing the power of the classifier. So this is the multilayer perceptron, which is basically adding all those neurons in layers and stacking the layers together. The multilayer perceptron, we can call the part where we have the input values. This is the input layer. It's not really a layer of neurons, it's just the input values. And then we have layers of neurons, any number. We call them the hidden layers because they are neither the input nor the output. It's like it's the inner part of the model, of the network. And then we have the last one, the last layer. In this case, I only have one neuron in the last layer, but you could have more than that. We'll see those details because it depends on whether you're doing a classification only between two classes, then you just need one neuron. If you have more than two classes, you need more neurons, and depends. If you are trying to generate an image, you need convolutional layers and things like that. So we'll cover those details, but for now, just consider this simple network. So in this case, instead of having just one neuron and the two inputs, we now have three neurons, two of them in the hidden layer and then one in the output. So multilayer perception is also called a dense network. These are dense layers because they are fully connected between one layer and the next, and you get a dense network of connections here. And it's all feed-forward, so all the values are being propagated from the inputs to the first layer, second layer, and so on, and they stop at the last layer. And you can have any number of hidden layers. You have the output layer and the input layer. So how can we compute the changes to the weight on these neurons here? For the last one, it's the same thing. So we have an output here, we can compute the error, and we can, from the error at the end, we can compute the derivative of the error with respect to the output of that neuron, and then chain it back to the derivative of the output of the activation function and the weighted sum of the inputs, and so on until we get to the weight. The difference is that for the last neuron, the inputs are not really the inputs that we feed the network, but are the activation values of the previous layer. So this is just like if this was a single layer network that is receiving as inputs the outputs of the layer before. But the equations are the same. It's just that instead of this x value, what we have is the outputs of the previous layer. But then, for the layers that are behind the last one, note that we're going from the output layer and we're going backwards through the network, so that's why it's called backpropagation, the algorithm. What we do is we continue the derivative. So we computed the derivative of the error for the output layer with respect to its activation, then go back to the sum of the inputs multiplied by the weight, then for the contribution of each of the weights, and then we go through that connection. So in this case, we computed the derivative all along to the weight that multiplies this input, but we can go back through that connection and keep computing the derivatives all through this neuron and then any other layers we have.
During backpropagation, we have single percent of the multi-layer perceptron, or we only have one multi-layer perceptron?
Well, if you have the perceptron, you can use the original training rule for a single neuron. If you have one neuron with a sigmoid activation, you can use the methods for logistic regression or something like that. But this idea of propagating the error backwards, you can use it with one neuron or with many. So the difference that backpropagation made was that it enables us to train networks of neurons. Without backpropagation, you can still train one, but this is the method you need for training one. But you can use backpropagation for a single neuron by doing it this way. So we compute those derivatives all through these connections and go back through the network. So if one neuron happens to have several neurons in front, in the next layer, then we actually have to sum the contributions of all the layers in front to that neuron, but then we keep computing the derivatives and going back all along through the network to compute what changes we need to make to the weights to train the network. So the intuitive explanation here, suppose we have one neuron here that is in part of a layer, and it has two neurons in front, and these are output neurons in the output layer. So each one of these neurons would have an error here. We compute the derivative of the error with respect to the output, and then the weights here, all the way until we get to this neuron for this one. Do the same thing for this one, and add the two together to keep to keep propagating the error backwards through all the weights. So by adding all of these things, we can compute what contribution each weight has to the gradient of the error function, and so figure out how to change each weight. But one thing that I would like to point out, so if we are using sigmoid activation and quadratic errors, then we get these particular equations. But if we use other activation functions and other loss functions, we simply get different equations, but the principle is exactly the same. We are computing the derivative at each node, at each operation, and chaining all those derivatives together. So for the general case, what we need to do is we input the example in the network, and we compute all the activations forward. And then we go back by computing the derivatives of all the operations involved in the network, of all those sums, the products, the activation functions, the loss function, and so on. We compute all the derivatives. And you can imagine that as long as we know how to compute the derivatives for each individual operation, then we can easily automate this for any kind of architecture or network, because we simply have to change those derivatives to compute how to change each of the weights. So this would be the general idea: use backpropagation over all the network, and it's always doing the same thing, chaining the derivatives to find out the direction in which we have to change the weight to reduce a bit the loss function. And then we do that with batches, with stochastic gradient descent, and we train the network like this. So this can be easily generalized for different architectures, different activation functions, different loss functions, and this is basically what you can do in TensorFlow. TensorFlow includes the autodiff algorithm to compute the derivatives automatically, and then you just chain all these functions together and you run the optimizers. So then for the next few weeks, we'll be looking at these different combinations, different kinds of optimizers, activation functions, and so on. But the general architecture will always be the same. So how does this work? If we train this network, so we have an output layer, we have a hidden layer, and the same inputs as before. But the last neuron is not seeing the input directly, it's seeing the output of the hidden layer. And since these neurons can output nonlinear functions, they have a nonlinear activation function, they can squeeze the data in different ways. They do that nonlinear transformation. So this is what the output neuron is seeing along the training, and these are the outputs of the hidden layer. And as you can see, as the network is learning, the hidden layer is starting to separate the data, so that even though the output neuron can only do a straight cut on this data, it's not doing a straight cut on the original data, it's doing a straight cut on the transformed data. So this is the same idea that we had with support vector machines and so on, that we do this nonlinear transformation, but now we are learning this along the network. And this allows us to, by increasing the number of layers, the number of neurons and so on, increase the power of the model to classify. If we add other neurons, for example, in this data set, I just have a curved frontier between the two classes. In this one, I have one class surrounded by the other, and then I added another hidden layer, and you see that it takes a bit longer to learn because we have to propagate the errors through more layers. But you have these transformations in the hidden layers until the last one can just cut this straight and separate the two sets in that way. So by chaining together neurons, as long as they have a nonlinear activation function, this is important because without that you can chain them together and it still works as a single linear transformation. Yeah? Well, these are latent space representations, yes, so inside that. But usually the name is given for things like autoencoders and so on for a specific part we're interested in, but you can apply the concept in general to these different internal representations of the network. Yeah. So, how can we solve complex problems? We just take a bucket full of neurons and start adding things. Well, there's a bit more to it than that, but this is the general idea. If you stack enough neurons, you get a powerful model and more powerful and so on. Of course, eventually you start overfitting, so you need to take care of the data. And then there's a lot of clever ways of minimizing the number of parameters while keeping the same kind of power, and we'll see that with convolution networks and so on. But the general idea is that since you can apply the same kind of algorithm regardless of the architecture, you can just pile on neurons to solve increasingly complex problems. So how does this differ from what I'll call the shallow models of classical machine learning? So linear models, you just choose yourself the features, you have a linear classification, and you can only separate things if in the space of the features the classes are linearly separable. With more powerful models like support vector machines, for example, you have this intermediate step of nonlinear transformation that allows you to increase the power and then adjust the frontier to whatever shape the data has. But still, you choose the features, you feed it to the model, and it does the transformation that you specify, and then it does the linear classification at the end. With deep classifiers, this becomes quite different. You can have extremely deep networks with lots of different layers that do different things at different steps, and that you can adjust the architecture in the way that maximizes the ability to learn the appropriate features. So you can just, if you want to use support vector machine, for example, for classifying images, you have to convert first the images into a table or a vector of numbers that have some meaning, like the overall color, the brightness, the number of edges, things like that, and then you feed the support vector machine. But if you want to do that with a deep model, you can just feed the image, and the different layers will try to figure out what is relevant for the classification. And this makes it very different in where you're stacking nonlinear transformations so that you don't have to worry too much about the initial features. The network itself will learn what features are useful and will short circuit that step where the data scientists have to think about the features. So how does this work? This is an example from convolution networks. And this is a method of visualizing what the kernels are doing. When we reach the lecture for convolution networks, I'll give you a bit more details and explain better what you're seeing here. But for now, this is a representation of the kinds of features that different layers are identifying in the images. And the first layer identifies things like horizontal edges, diagonal edges, colors, patches, and things like that. So they are relatively simple and simple elements of the image. But then, since these are fed into the next layer, and the next layer is looking at contributions from the activations of these different filters, it can actually respond to things more complex like circles or parallel lines and so on, until you get things that already look like a balloon or an eye or something like that. So as you stack these layers, they start identifying more complex patterns in the images. And since all of this is learned from the data, eventually these layers will respond to relevant aspects of the image to perform whatever classification task or regression task we want it to perform. And that's how feature extraction is learned in the deep model. So by getting these efficient representations, it's effectively automating the process of extracting features. So what does this help us in unstructured data? So the course is called Learning with Unstructured Data. It turns out to be deep learning. We are not going to worry too much about the data being unstructured, although in many examples it will be. But I will take this lecture just to connect the two things together, because in the machine learning course you dealt with structured data. This is data where you can put everything in a table, and each feature has a specific meaning. For example, even when in the problem of identifying fake or true banknotes, we were using measures of entropy, or wavelets, transforms, and so on from the images, and we are not using the images themselves. And each of those columns has a specific meaning. So you can have age, height, weight, things like that, and all of those features are fixed. So this is structured data. You can put a table with the right column. Some data is structured, but usually maintaining structured data requires constant human intervention. You have to keep the databases updated, you have to retrieve this information, or people have to input the correct information at the right time. This is very good for machine learning because you have the different features, you feed them into the model and you get some results, but it requires constant maintenance, and it turns out to be a very small part of the data. So basically there is this estimate here that 80 or 90% of useful data is unstructured, does not follow that structure. Of course, this is probably just a number that they took out from their head because there's no way to actually compute this. But the idea is that most of the information is in forms that are not completely structured. They can be semi-structured data, so you can have something that has some structure, for example, XML records, or a log from the server, something like that, where you can identify different fields, but they are not in the same vector, they don't have the same size, there's a number of features, different examples can vary a lot in their structure. You can also have the mixture of structured and unstructured. For example, you can have a database with a table where people insert numbers and categories, and then you have a comments field, and then that is basically unstructured there in the middle, and you don't know how to use that. So even when the data has some structure, but you don't have a fixed number of features and a constant relation between some meaning of the values and the feature there, something that you can put in a table, it becomes harder to use machine learning here. And most of the data is actually unstructured, which is things like text, video, sound records, things like that. And it's unstructured because if you imagine an image, you still have a vector of values because you have the height times weight times the number of colors, and you can put everything in a vector. But the position number 312 in that vector can be part of someone's hair, or part of a shoe, or a pixel that belongs to the cat, and it doesn't have always the same meaning. So you cannot just put everything on a table and have some confidence that pixel 312 is important for something, because it's changing position all the time. So this is the example of unstructured data. You can create numerical vectors with that, but you don't have a fixed relation between the value in the vector and something that has meaning, some feature. So most data will be in this form because this is actually how most data is generated. People take pictures, write comments on Facebook, or upload videos for YouTube or something like that, and they are not putting everything in the table. And even inside the structured data, you can always find some exceptions where you have some items of unstructured data. So this would be difficult to use with classical machine learning because you would need to extract the features yourself. So the classical approach will be to find some methods to explicitly convert the unstructured data in some kind of structured data. For example, in text mining, you can find words, create vectors with counting the words in the document. You can cluster words that have similar meanings and so on, and create some kind of extraction algorithm that converts text into a vector with meaningful features. You can do that for images, you can count how many circles it has, or the distribution of colors, or do histograms, or things like that. But this usually takes a long time to perfect methods for extracting features, and they tend to be very fine-tuned to specific problems, to a particular language, to some kind of images, and so on. So it takes a lot of work and a lot of time to do this. But this is not a good way of doing things if we're thinking about the goals of artificial intelligence. The idea is to put the computer to do all this work and not humans. So if you use the classical machine learning approach, where humans need to choose the features and extract them and then do some nonlinear transformation for classification, you're falling outside this kind of paradigm of passing the work to a computer, and it becomes a problem, especially when you need to quickly respond to changing conditions. For example, in adversarial situations where you have some methods for detecting credit fraud, but the people who are committing credit fraud will adjust their behavior to avoid detection. So if your method cannot change quickly, then after a week it's useless and they all make a lot of money out of you. So you need to be able to respond quickly to those changes, and this requires automating these steps. And that's where deep learning can have a lot of success, because it automates the extraction of the adequate features. And it can do this even without labeled data. So this is a classical example of an autoencoder. We'll cover autoencoders in more detail later on. But the idea is that we have a neural network that receives 8 inputs. So each row here is one example. And the inputs can be 1 and all zeros, or 0, 1 and all zeros, and so on. The network has 3 neurons in the middle part, and then it has again 8 neurons in the output. And when we start without training the network, then it's not doing anything much, but we want to train it so that it outputs the same as the input. This is the idea of the autoencoder. You train the network to echo the input. But it has to do that using only 3 neurons in the middle part. So we are constraining what the network can do. And this can be trained without labels, because since we only want an echo of the input, we can use any data set, even if it's unlabeled. We just want to see if the network can replicate the input. So after training, we get something like this. When we input 1, 0, 0, 0, and so on, we get the same output. When we input this one, we get the same output, and so on. So the network is not doing anything useful, apparently, because it's just giving us back what we input. But we trained on this set of examples. So it's learning about this kind of data, not any combination of 0 and 1s, but just this set. And what it did in the middle part is to create an encoding for the 8 different values using combinations of zeros and ones here. So you see, these are all in a random order, but you have 1, 0, 1, 0, 0, 1, 0, 1, 0, and so on. You have 8 different combinations that the network learns to encode the 8 different inputs it's receiving. So this is one way where we can use these kind of models, neural networks. If we use deep learning, we can do this in a more complicated way to try to figure out how the data is actually distributed in a more meaningful manner. So learning the manifolds for the data. This is a more useful example. We have this data set with fake and real banknotes. Each banknote is characterized by 4 numerical features that were obtained by scanning the banknote and measuring statistics on the image. If we try to project this into 2 dimensions using a common statistical method, principal component analysis, which is basically choosing the 2 directions where the variance is largest, we have this result here where the points are, the 2 classes are very mixed together. But we can train an autoencoder which receives the 4 inputs for each example, then has 6 neurons, 4, 2, then again 4, 6, and as an output of 4 at the last layer. And we train this just so it gives us back the same thing we put in. So we don't use labels for this autoencoder, we are just training on the feature values of the banknotes. But when we use that and project into the activations of those 2 neurons there, which is these 2 dimensions, we have the 2 classes almost neatly separated because the network found the best representation for this data set.
The use of the PCA is just to reduce the computational time?
No, the PCA is just a comparison. So the network is not using PCA. This is just to show, because PCA is equivalent to this if you use only one single hidden layer and only linear transformations. So PCA is a linear way of doing manifold learning. The deep network, the autoencoder, is non-linear, so it's a lot more powerful and it can get you a much better representation of the manifold for the data. But this is just for comparison between the two. Yes. So this is trained with the data, so all the data sets, until it learns. Of course, if you want to check for overfitting and so on, you should have a validation set. The same thing applies as usual. But the PCA here is not done as part of this. It's just a comparison. Okay? So you get better results than with PCA. So with deep learning models, you can have the model itself learn how to extract the features, and you can do this even with unlabeled data, because the model can learn how the feature combinations are spread out in feature space, even without the labels, because that's the kind of examples that it will have to deal with. So this can be very helpful to find the best features for training. And this is done because deep models can learn to encode the features in useful ways. So if you have all your data set labeled, you can train a deep classifier that will encode the examples in the best way and learn that encoding as it learns classification. If you have some examples labeled, but many examples that are not labeled, you can add something like unsupervised deep learning to find where the actual examples are distributed and then learn the features from that. Okay? So all of this is done automatically and can greatly speed up these kinds of problems, solving these kinds of problems. So why did deep learning appear now and not in 1950 something with the perceptron or something like that? So there are several conditions that had to be met for the success of deep learning. First of all, With deep models, you have lots of parameters, tens or hundreds of millions of parameters or more than that. So you really need a lot of data to avoid overfitting. You probably need very complex models for hard problems to solve. You cannot solve problems like classifying images or something like that with a few parameters because it's a complex problem. But if you have a complex problem that requires a very powerful model, you also need a lot of data. So basically, we can think of classical machine learning problems as performing better when you don't have much data, because they are simpler. But then, as the problems get more complicated and you have more data, you cannot get much out of them. They stabilize after that. And eventually, deep models become better because now you have enough data to train very complex models. And because of that trick of chaining together neurons, you can do arbitrarily complex models with neural networks. So in 2006, for example, these contests for trying to figure out the best algorithms for categorizing, classifying images, they had this data set which had about 101 different categories, and each category had on average about 50 images. So it ranged from 40 to 800, but this was the size of the data set. 100 categories and a few tens of images for each category. And for this, even though convolutional networks had been in use since the late 90s, up to 2006 were classical computer vision methods that used algorithms for segmentation and computed histograms and so on, and used classical machine learning. These were the ones that worked better with these data sets. But then there were some improvements, both in methods. First with pre-training, we'll see a bit about that later on, but especially with this kind of activation, rectified linear unit, which greatly speeds up learning, and also hardware. The first general-purpose GPUs, which greatly speed up the kind of computations that we need to do. We'll see that more in detail next week, and also specific processor units that are built right now. Google has this tensor processing unit that is specifically designed for deep learning, and also Intel has this Intel Nirvana unit. So we start having hardware that is designed specifically for deep learning. And we have more data. So in 2012, this ImageNet database appeared. It has 1.2 million images and 1,000 categories. So it's one order of magnitude larger than the previous one. And when this came up, then deep convolution networks dominated the field. So in 2012, the first year, this AlexNet achieved 15% top 5 error. So this is the top 5 error is you take the top 5 predictions of the network. So remember, there are 1,000 categories, so you're taking only the top 5 the network considers the image to be assigned to, and this network missed 15% of the images in classifying in the top 5. But then, for each year, they started reducing 15, 13, 7%, and so on, and currently it's about at the level of human error. So at some point, the network is making mistakes because the actual data has mistakes, or there are things that are ambiguous. If you have images of clouds and mountains and so on, there are some that maybe they have clouds and mountains and it's not very clear. So currently, for this kind of problem, at least in this data set, we are reaching the level of human error, so it's no longer meaningful to reduce error there. And all of these are deep convolution networks. So after this point, when we have enough data, there is no other technique we know of that can beat deep convolution networks for image classification. So just to give you some examples of what we can do here, this is the AlexNet, the one from 2012. This was trained in using two NVIDIA GeForce 580 motherboards, each one on graphic cards. Each one only has 3 gigabytes of RAM, so they had to split the net into two. This is one half, and then they had another half, and they were training the two in parallel. And these are convolution networks. We'll see more about them later on, but basically you have different layers with a number of filters. Each filter corresponds to one neuron that scans through the image, but then you have this number of inputs here, so 150,000 and 250,000 and so on, and you have lots of millions of connections there that you have to adjust. So this is so large that they needed 2 graphics cards because 3 gigabytes were not enough for the model, and they had to split it in 2. But with enough data, they could train it adequately and have a good result. Then a few years later, this is GoogleNet. This has 22 layers, but these are layers of inception blocks. These inception blocks, we'll see them in more detail later, but they include several layers of convolution, several convolution layers, which do different things. And you can see the architecture is quite sophisticated. There are some intermediate outputs here that then are used to help with the final classification, because this solves some problems of starting to lose information on the gradients when you have a network that is very deep. When you do that backpropagation and you have to change the derivative, if you put many layers, then you start losing information and things start disappearing. But you can add these kinds of short circuits to help train the network and to get intermediate information from the intermediate layers and so on. So this is just to give you an idea. We'll see these kinds of things more in detail later on in the course. But this starts getting very sophisticated in the way the networks are arranged. One different example to cross with text too. This is a paper from 2016 to generate explanations for image. So visual explanations are legends for the image, where it specifies what kind of thing you have in the image and explains why it is identified as that thing. So this was done with images of birds, and the idea is they have 2 metrics here that they are trying to measure. So basically, if the words are correct and if the classes are well discriminated between the kinds of birds. So one convolution network was extracting features from the bird images, identifying patterns, and this was being fed into 2 LSTM recurrent networks. So these are long short-term memory. They have a peculiar architecture, but basically they receive as input the output from the previous iteration. It's the same network, but it's recurrent. It's receiving its own outputs. So you can imagine if you unroll it, it's as if it's a chain of nets, but they are all the same. They have the same weight. And the architecture here has some path for passing the value onto the next iteration, for forgetting the value, for adding new information, and so on. So basically, this is something that is used to process sequential data and can also generate sequential data. And they use 2 of these to generate, to examine both with the features that come here and the previous word, generate features that the other network would use to pick the most likely words that would follow. So it would generate a sequence of words, remembering the words before and the features obtained from the image. So long story short, you get, this is a complicated relation between the different networks, but you get things like this. This is a pine grosbeak because this bird has a red head and breast with a gray wing and a white wing. So this is an automatic explanation generated from the image. Of course, they chose some good examples. There are probably bad examples there, but it can do things that actually make sense, combining what the convolution network is extracting from the image and then what the recurrent networks have learned to generate sequences of words from examples given by humans for training. So what can we do with this? Well, there's a lot of things to do. I'm just finishing today with an example or 2 examples of generating visual data. So in this case, you can see, if you search online, NVIDIA has a demo where they have convolution networks generating the landscape, like simulating driving, and they have just a basic model for where the cars are and the walls and so on, and the network does all the rendering by making up the colors and the textures and so forth that it learned from actual video. And you also have generative adversarial networks used to create faces of people that don't exist, or even for fashion, the fashion models, they are not real, just the images are generated by the network. So there are lots of applications for this. There is one question of where we are in the hype cycle. So basically, the hype cycle is this idea that when a new technology comes, everyone is very excited because it will solve all problems, and then everyone gets disappointed when it doesn't solve all problems, but eventually things stabilize and we start taking advantage of it. So the question is, if we already went through this phase, there was a very bleak phase for artificial intelligence and neural networks. If we are already on this side and this is more or less the end result, or if this is still increasing, or if we'll be disappointed because then we figure out that we're doing everything wrong in some way or something like that. So this is just an open question at the moment. So I cannot assure you that this course will be useful in the future. Basically, it's not my fault if it's not. Okay. So things you can do until next week. There is this TensorFlow playground that you can use to create different networks and then train them and see visually how things are working. This is not particularly useful for any particular end, but you can do this just to play around a bit and help understand what the different layers are doing, because you can see visually how they are separating the classes and so on, and how you get the result. You can also choose different activation functions and see the difference between them, so you can experiment with this a bit. But for homework, I'll ask you to, we don't have the tutorial classes this week yet, we'll start next week, but I ask you to get everything ready before so we can start with the exercise. If you want to use your own computers, you can install or update Anaconda. If you don't have Anaconda, install the latest version. If you have, just check if it's sufficiently recent for installing TensorFlow 2. And it's easy to install in Anaconda. You just use the Conda installer. If you have a CUDA compatible card from NVIDIA, for example, then you can install the GPU version, which can be considerably faster, depending on the memory of the card and the card that you have, but it can speed up things a bit. So in that case, you install TensorFlow dash GPU. If you don't have a compatible graphic card, just install the CPU version, which is the second one. So choose one of these to install after installing Anaconda. So this uses the Conda installer and puts everything in the same environment. You should also set up Google Colab, because if you want to use the computers on the lab, they are outdated. The TensorFlow is one something. So if you want to use those, you should log into Gmail and use Colab. This is free, and you have 12 gigabytes of RAM, and you can use it for free, I think for 12 hours a day or something like that. There are some limits, but it's okay for the classes and for this. So all you need to do is log in with your Google account with Gmail from the university or something like that, and then go here to the Colab, start a Jupyter notebook, and just do these first 2 lines at least. So this imports this drive module and then mounts your Google Drive. And this will ask you to authorize the connection between the Google streaming service and your Google Drive. And once you authorize that, you can write your Python code and have access to the data in your Google Drive. So this is useful for uploading the data and uploading the scripts and so on. Then what you can do is you should set the TensorFlow version. This is a magic command for IPython that sets the version to 2. So this you should do every time you run your script. You also need this to map the Google Drive, and then you can change to whatever working folder you want. So you can include this at the heading of your notebook, and this way you can always use one of your folders. So you will do this every time in the lecture, but you can just check in the tutorial, but you can just check if this works, and you need to authorize it once in order to be able to do it. After this, you can either upload your scripts and just use run to run your scripts, or if you prefer IPython, or if you prefer Jupyter, you can do everything in Jupyter. I personally don't like Jupyter because it encourages very messy code where we copy paste and have the different cells. But I'm old and you're not, so maybe that's the problem here. So either way, you can use Spider to write your code and upload to Google Drive, or you can use Jupyter with Colab. This, in case you don't want to use your laptop. If you want to use your laptop, you can just install TensorFlow, or you can do both. If you see that things take too long to compute in your laptop, or it gets too hot or something like that, then try Google's computers instead of your own. So to sum up, we saw a revision of this of backpropagation, and now generalizing to any kind of architecture and activation functions and loss functions and so on. So basically, if everything can be the derivative can be computed for all of these functions, we can just chain all of this backpropagation together, and it's done automatically in TensorFlow. The reason why deep learning is the success is so recent is this combination of specific algorithms, of hardware, because it takes a lot of computation power, and available data. It needs a lot of data to avoid overfitting with this kind of model. So take a look at this paper in Nature. It gives you an overview of deep learning. And this part, chapter 5, is just on machine learning. It's the same I recommended for the previous lecture. But you can look at all all section 6, because it's backpropagation and so on, not just these two first sections, and also chapter 2 of Deng's book. So